All right, moving on to lecture 8.3. A lot of similar concepts, but you can see this is a doozy with 73 slides, so we are going to be breaking this one up out of necessity into two parts. So we'll get a good start here right away and see what we can learn about this Ka and Kb. I think you can probably figure out those are going to be equilibrium constants for acids and bases. And then we're going to get into a really good challenge of what do you do when it's a weak acid, meaning that it's an equilibrium system. It's going to be going back and forth. You can no longer predict in a guaranteed fashion what the product is going to be. So let's start right away with this little combination of the NH4 plus, which is this ion, and I'm sorry. I'll be right back. I have to turn this. Okay. Sorry about that. So again, this reaction, you can see the ammonium ion is acting as if it's an acid because it donates its hydrogen to the water, and that means the water is acting as the base here and has a really strong, you can't get any stronger than this as a conjugate acid. So this base with that conjugate acid. And so now this becomes a conjugate base, which of course could accept a proton to go in that. So we've got a real back and forth thing going on. And now you have quantities on the bottom and the water, of course, out of play, and the equilibrium constant. So you call this a Ka, and this is the acid ionization constant. So how much does that acid ionize? All right. So strong acids will also have a Ka value. So something like hydrochloric acid, you know, is going to donate its hydrogen and to the water and end up being a Cl minus, which is now a conjugate base, could accept a proton theoretically. But you can see there's two products and one reactant that could be, in theory, part of a Ka constant. So when we look at these, HCl, a strong acid, really big, meaning those numbers on the top are quite large. All right? And as you get weaker and weaker with the acid, these Ka values get smaller and smaller. So one of the real strengths of knowing an equilibrium constant is if they're small, you're not going to get very many products. So as defining an acid, you say, wow, hydrogen cyanide really likes to stay as HCN and not give up that hydrogen at all. So that is what we're working toward for knowing these Ka values, because it does help us learn about how these acids are going to behave. Here is just the reverse reaction, so then we would talk about a Kb, because the primary reactant is now going to be acting as a base and accepting a hydrogen, sort of ripping that hydrogen off of the water, and then this acts as a weak acid to donate the hydrogen, making a very strong conjugate base. But these again are weak. You put the products on the top, the reactants on the bottom, and you set up what is known as a base ionization constant, or an equilibrium constant for the reaction of a base, and we just did acid. All right, so same thing, sodium hydroxide. I'm not quite sure, I'm going to look this up, why they couldn't write that very large number. It's bigger, maybe bigger than our national debt, and they couldn't write it because no longer numbers can define it. Basically, what you're looking at there is it approaches 100% ionization, and for all practical purposes, it will, because it's a strong base, be off the charts. Okay, so that's kind of what we're looking at there. And then as we get smaller and smaller, again, you're going to get weaker bases down here. The large numbers mean very strong bases. So those KB values can be very useful to us. Now, we can do a pKa and a pKb, just like we did pH and pOH. But we're going to do this with the Ka value. So what you can do is you can take the negative log of the Ka. That'll give you your pKa, just like pH. If you know the pKa and you want to find out what the Ka, just take 10 raised to the negative pKa, just like we did 10 raised to the negative pH. You can see why introducing with simpler hydrogen and hydroxide ions was really important, because now we're going to get a little bit more complex and deal with these equilibrium constants and still taking the negative log of these values. So we can work the problems in a very, very similar manner. That means if the pKa for HCN is 9.31, find the Ka value. Okay, so we did talk about Ka. We said, if that's a big number, it's going to be a strong acid. We didn't really talk about pKa yet. So let's go ahead and calculate this. Just raise that to the power of negative 9.31. Use your caret key, and you end up with 4.9. And you're like, sig figs? Yep, because this is a p. Remember, p is place value. So this 9.31 has two significant figures, which would give you 2 in your final answer. And then the Ka, no units, as is the same case with pH. So this is a numerical constant saying, yeah, you got a pretty weak acid there. The pKa value, as you can see, was relatively high. So those things are up-down, inversely related there. If you got a really big Ka, you got a really small pKa. All right? If you got a really small Ka, you got a bigger pKa. So the stronger the acid, the smaller the pKa. Sounds like pH, doesn't it? Smaller number for pH, stronger acid. Very closely related there. And that can be helpful. And of course, bases are the same way. Again, so strong, we're not even going to do numbers for it. But if you look, these bases, the stronger the base, the smaller the pKb value. Okay? So these smaller values here would indicate a stronger base. So it's opposite of what you have here. Here you have a really small Kb and corresponds to a larger pKb. All right? Okay, so you can see same thing as the Ka and pKa. They're opposite. As you get smaller, that means not a very strong base, and you will have a larger pKb value. Okay? Now, we can look at a chemical reaction two ways here. Okay, so if we look at ammonia, it can react with water to become NH3 or NH4 plus, or it can start as NH4 plus, react with water to become NH3. So these are opposite reactions basically, but you can see they're not just complete reverse reactions, because you have the hydroxide ion here and the hydronium ion here. But you can write a Kb for this reaction because it is acting as a base and making the OH. All right, sorry about that. That's, I think, my 5th interruption during this lecture. That's a new record. So anyway, you got a basic reaction and an acidic reaction, a Kb and a Ka. So I want you to kind of keep these in mind and see there are some similarities, obviously, and we're going to do on this next problem, we're going to talk about how you can line these up next to each other. So if you have the same compound and you do the acidic reaction for it and the basic reaction for it, look at what happens, and you can just see the potential. You're like, oh, I've got ammonium there and ammonium there. Those will cancel out. I've got ammonia and ammonia. Those will cancel out. And lo and behold, you end up with hydroxide ion times hydronium ion equals Kw. That allows us to make a comparison between Kw, which you guys know, you just take Ka times Kb gives you Kw, and do a little bit of excuse me, a little bit of manipulation here, algebraic manipulation, and just do the negative log on everything, and you end up with pKw equals pKa plus pKb. That should sound kind of familiar to you when we were doing acids and bases. So now, since we know that Kw equals 1 times 10 to the minus 14th, we can set this on a 14-point scale too. And if you know the pKa, you can figure out the pKb just like we did with pH and pOH. So it's a way of really relating equilibrium on these weaker bases to this using the pH scales. And instead of pH, we're talking about pK, negative log of the equilibrium constants. But it's a nifty little equation. And just taking a quick peek on the purple sheet right here, it says, you know, that Kw equals the concentration of H times the concentration of OH, which also equals Ka times Kb. So that is provided for you as an equation. And they do give you the definitions of what the negative log, that pKa equals the negative log of Ka, and so on. But this is this little leap right here is not provided for you directly. Okay, so you have to kind of go, well, I can figure that out based on this little comparison right there. So these two will add up to be 14. So anyway, so we'll make sure you look over that purple sheet, and we'll hit the pause here and do the next lecture.